So welcome back to the course page on the Fourier series, and today's discussion will deal with in more detail about how to represent a Fourier series in complex form. In the last class we have seen that we can synthesize any signal by using cosine and sine functions. These cosine and functions, the fundamental frequency plus the harmonics of the cosine and sine functions, and we can recreate or the sine wave. And we have seen one example also there. In the case of a square wave, we recreated a square wave, and we calculated the coefficients as a0, then an the coefficients, and bn, and we have seen in this case the coefficient of the cosine function is 0, and that's only the coefficient part of the sine function is available, and we created this square wave, and we calculated the coefficients of an and bn, and finally we got an equation as it's equal to 1 by 2 plus 2 pi pi into sine t plus 1 by 3 of sine 3t plus 1 by 5 of sine 5t, and we got a signal. We recreated a signal by using this, and here we have got a lot of coefficients for the frequency coefficients. All those are the frequency coefficients, and we created a sine wave, a square wave in time domain. This is in time domain, and we in the frequency to time domain. It contains only some frequency component parts, and so I would like to inform you that so for the frequency analysis is a very important tool, and we can split. You may familiar with this experiment by the Sir Isaac Newton, and we can split the white light into different colors of light by using a prism. And this is actually an analysis of Fourier analysis, and we can it's a frequency analysis. So we'll split the light into 7 different frequency lights with 7 different frequencies, and all these light color of light is having some frequency, violet, indigo, blue, and you learned in the previous classes in the physics class. Now that's one example for a Fourier analysis. And if again the Isaac Newton have done another experiment. If you combine all these 7 frequencies or 7 lights by using another prism, if you place a free prism in this place, then we can recreate a white light again. And moreover, he has done another thing also, and he placed a prism here, and this prism will combine all these light, these different colors of light into one, and again he inserted one slit here, one and masked one color of light. Say for example, if you mask a blue or violet in this place, then the combined light will be something different of a white light. And that's one easiest method to understand how the Fourier analysis and synthesis works. This is what actually the Fourier analysis is. We analyze these signals into different colors of light, and again we synthesize these different frequency components into one. That's another example, one example. And here is another example. You may familiar with these musical instruments with some different notes, C1, C2, C3, C4, etc. Different notes are there. And again, if we have different frequency components here, and in this case the fundamental frequency is f0 is 8.176, and again if you take the fourth harmonics is here. This is the fourth harmonics of the fundamental frequency. If any device, if you place a, say for example, if you are playing a violin, like a violin type sound in a piano, and if you can play different sounds or just like of a guitar or something like those, and the fundamental frequency is here. We set a fundamental frequency here of that music, and then C1, C2, and C3, C4 are all those are some harmonics, and C1 contains the fourth harmonics, and here it contains the eighth case value of k is 8, and here it is 16, and here it is 32, and 64, and 128, and 256, and 512. That looks very nice, and it's another example for to illustration of this frequent Fourier synthesis. We'll combine the frequency components. Okay, so here we have used the components like for the synthesis and for the analysis. His synthesis equation, here we have used a0 plus a0 by 2 plus cos components and coefficients of cosine functions and coefficients of sine functions. Now and fundamental frequency and harmonics, and how to represent this in complex form instead of using this cosine and sine. We know the relations from the Euler's identity, that e raised to j omega n omega 0 t is equal to cos plus cosine n omega 0 t plus j sine n omega 0 t, and e raised to minus j n omega 0 t is equal to cos n omega 0 t minus j sine n omega 0 t. Or we can write cos omega t as 1 by 2 of e raised to j omega t plus e raised to minus j omega t, and sine as 1 by 2j into e raised to j omega 0 t minus e raised to j omega 0 t. So this can be utilized in the if you replace this instead of a cos and sine, if you replace it by its exponential functions, so complex exponentials, and this is the equation f of t as cosine and sine functions. Instead of cosine and sine functions, we replaced by using its corresponding exponentials. So here we simplified the equation, and we obtain and replacing Cn as an minus jbn, and 1 by 2 of an plus jbn as c, the conjugate of that function. So we got a complex exponential equation, the complex form of the Fourier series, as f of t is equal to summation minus infinity to plus infinity Cn e raised to j n omega 0 t. So this is the equation that we normally used in practical applications for the analysis and the synthesis of a Fourier series.